Good morning, everybody. Today, you guys are going to be learning about gases. You should have just corrected your gases POGL, and now we're going to be doing our gases notes. Okay? Just going to make sure that everything's working. All right, everything's working. Okay, so gases. In your POGL, you guys would have learned that gases exert pressure. Okay, the reason why they exert pressure is because gas particles are in constant motion and they are colliding with each other as well as the walls of their container. The more collisions with the wall of the container, the higher the pressure. Okay, there are a couple other variables that affect the magnitude of pressure that a gas exerts, and those magnitudes are the number of molecules. So if you increase the number of molecules in a container, you're going to increase pressure. The volume of the container, so how large or how small the container is, and then the temperature of the gas. Because if you increase temperature of a gas, the particles are going to increase in energy, and then they'll also increase the number of collisions, increasing the pressure in the container. Okay? All right. So gases can behave one of two ways when they are in a concentrated area. They can either go through diffusion or effusion. Diffusion is when a gas goes from an area of high concentration to an area of low concentration. A great example of this is if you think about burning a candle, or if somebody sprays a couple spritzes of perfume or cologne, eventually the whole room can smell that scent. The reason why the whole room can eventually smell that scent is because the scent molecules go from an area of high concentration to an area of low concentration. So the scent will spread. Gases do the same thing. Gases don't stay in a concentrated area. They will diffuse from an area of high concentration to an area of low concentration. Another behavior of gases is effusion. Effusion is similar to diffusion, except it's when gases are passing through a small barrier or tiny opening. If any of you have ever had a flat tire, you have experienced effusion, because the gas inside of your tire is slowly escaping or effusing through that small hole that the nail or screw or whatever made in your tire until your tire is flat. Okay. Another good example of effusion is when you're breathing. As you're breathing air in, gases effuse across the boundary of your capillaries or your blood vessels. So the oxygen will go from inside of your blood vessel, pass over that boundary of your blood vessel wall into the cells of your body. Okay, that's another good example of effusion. All right. So now that we know what pressure is, we're going to talk about how we measure it. We measure pressure using a tool called a barometer. Okay, a barometer measures barometric pressure or atmospheric pressure. It was a tool originally invented back in the 1600s by Evangelista Torricelli. There's a picture of Evangelista Torricelli's barometer here on the screen. You're going to want to be sure that you draw a picture of that barometer in your own notes. A couple things that I want to point out to you about that particular barometer. Hold on here. Okay. So this particular barometer uses liquid mercury, a shallow dish of mercury, and then a tube that was hollow that was inverted or flipped over in the mercury. Okay. So a couple things to notice are the fact that the top of the tube has a vacuum in it. That means there's no air, there's no liquid, there's nothing in that space. The other thing to notice is that the only part of the mercury exposed to the atmosphere is the surface of it here. So what happens in a barometer is the atmospheric pressure or the air pressure pushes down on the surface of the mercury. And then because there's no other place for the mercury to go, it pushes the mercury up this tube until the mercury level reaches the point at which the force of the mercury in the tube and the force of the air pressure are equal. So that's how you can measure air pressure using a barometer. You guys are going to watch a short video now that goes over the history of the barometer and the discovery of the barometer, and gives you a little bit more detail. As you watch that video, there's some space in your notes. You guys should be taking some notes about what barometers are, how they work, who discovered them in that space on your notes. Okay, so pause this video here, switch over to the video on barometers, and then we'll return to our gases notes in a minute. All right, so now that we've gone over barometers, you guys watched that short video about Evangelista Torricelli, who made and discovered the first barometer. Now that we know about the tool to measure pressure, we need to also go over the units of pressure. There are several different units that physicists and chemists can use to measure pressure within a system. The first is atmospheres, or ATM. The second is millimeters of mercury. We get that one from the barometer. The third is torr. The fourth and fifth are similar just because they're different by a factor of 1,000, but they're pascals and kilopascals, or kPa. And the last one, if you've ever filled your tires in your car, you've interacted with, is PSI, or pounds per square inch. The numbers I've included on this slide are the conversion factors that you can use to go from ATMs to millimeters of mercury to torr to pascals, kilopascals, or PSI. So in a couple slides here, I'm going to have you guys practice doing a units of pressure conversion. This is where you would get those values. So be sure that you've not only written down the units, but the numbers as well, because the numbers are your conversion factors that will help you convert from one unit of pressure to another. Okay, so take a second here and record your units of pressure and then those conversion factors. All right, so now that you guys have written down those units as well as the numbers associated with them, we're going to continue here. Okay, so because pressure and temperature can both change, physicists and chemists have developed something called standard temperature and pressure, or STP. They've developed this so that there's a common language when dealing with a constant temperature and pressure. So if a physicist or chemist would say that this experiment was run at STP, there's an understanding that that means it was run at 0 degrees Celsius and 1 atm of pressure. It's important that you guys know what STP is, because in some word problems coming up throughout this unit, it might say, assume that this experiment was run at STP, and you will need to know that that means 0 degrees Celsius and 1 atm of pressure. So be sure that you have this written down in your notes as well, that standard temperature and pressure is 0 degrees Celsius and 1 atm of pressure. All right, so there are 2 practice problems in your notes now. I'll take a couple minutes, and I want you guys to do both of those practice problems. They're both problems converting between units of pressure. So you're going to use the units that you guys just wrote down to convert from one unit to another unit of pressure. If you need examples, I'm going to leave these examples up on the board for you while you guys do that. Once everyone is done doing those 2 example problems, you guys can go over the answers together as a class. 2 of you can write your answers on the board if you want, whatever Mr. Balin you guys want to do, but you do need to go over those 2 answers as well as the work to convert from one unit of pressure to another. So take a couple minutes now, do the 2 conversion problems, and then go over the answers. All right. So it is important that you guys do know how to convert between those units of pressure. You do not need to memorize all of those numbers and units, but you should be comfortable when given the conversion, setting up, a T-chart and converting from one unit to another unit of pressure. Okay. All right. So the next thing we're going to talk about is something called Dalton's law of partial pressures. Okay, and then we're also going to be discussing the magnitude of air pressure. So if you look at this slide, what this slide shows you is the composition of the air you're breathing, right? So as you breathe in, you're not just breathing in oxygen. You breathe in oxygen, nitrogen, carbon monoxide, as well as argon. And each of those gases composes a different amount of the air you're breathing in. So if you look, most of the air you're breathing in is actually nitrogen. Only 20% of the air that you breathe in is actually oxygen. Because each of those gases makes up a different amount of the air you breathe in, each of them exerts a different pressure on you and your environment. And so if you look, here's the percentage of the air you're breathing in per whatever gas we're looking at. So nitrogen makes up 78%, oxygen makes up 20%, carbon dioxide about 0.04%, argon and a few others about 0.93%. So because they make up different percentages of the air we breathe in, they exert different pressures on us. When there's a mixture of gases and you want to know what the total pressure of that mixture is, all you have to do is add up the partial pressures of each gas within that mixture. That's called Dalton's law. We'll talk about that in a little bit. Okay. But I also want to continue talking here about air pressure. So we just looked at the composition of dry air. So what gases make up the air that you're breathing that makes up our atmosphere? Air pressure that you're experiencing at sea level is roughly 14.7 pounds per square inch, which means that for every square inch of surface area on something, the atmosphere exerts about 14.7 pounds of pressure on that surface. Okay, you might not understand the magnitude of that, but if you think about like a 15-pound bag of potatoes, that's roughly 14.7 pounds. That's how much pressure in 1 square inch of space the atmosphere is putting on 1 square inch of surface area. Well, if you look at a typical object, most things are larger than 1 square inch. And so the atmosphere puts quite a bit of pressure on us and on the other objects on the Earth's surface. And so what you guys are going to do now is you're going to watch a video clip. It's on a DVD. It's called Newton's Apple. It goes over several different examples that show you how large the air pressure is from our atmosphere. It's kind of an old clip, so I apologize in advance. But it goes over, like I said, several examples to show you how strong and how large the air pressure of our atmosphere actually is. Okay, so you're going to pause my video here and then watch that DVD clip. It's roughly 7 minutes long. After you guys watch that clip, we'll continue and we're almost done with our notes for the day. All right? All right, look who woke up. Okay, so you guys should have just finished watching that Newton's Apple clip. A couple quick reviews of what you guys just watched. So the first one that I want to talk about is the tug of war. So when the tug of war was happening, what that was illustrating to you was the strength or power of air pressure, because that rope in the tug of war actually wasn't a continuous rope. It was 2 ropes that were each had a disc at the end of it, and between the 2 discs, the physicist created a vacuum, so he took away air pressure. So because there was no air in between the 2 discs and there was a vacuum, the air pressure from the outside air was actually pushing against the outside of the discs, pushing them together. And so those football players were actually trying to overcome the power of air pressure that was pushing against the outside of the discs. Okay, so you notice that they weren't able to overcome that power of air pressure. So that was a good example to show you how strong or the size of the force of air pressure from our atmosphere. The other example I want to talk about is the steel drum example. So in that example, what that physicist was doing, he had put a whole bunch of water in that steel drum and then heated it so that it was boiling and steaming. Eventually, the steam gas replaced all of the air within that steel drum, and then he sealed the steel drum off. Then he began cooling it, which when you cool water vapor, you all should know from our discussion last week what happens when water vapor gets cooled. It condensates and goes from a gas to a liquid. But within that sealed steel drum, if that water vapor condenses and goes from being a gas to being a liquid, there's no more gas inside the steel drum. And if there's no more gas inside the steel drum, there's no internal pressure. So the only pressure that steel drum was experiencing was the external pressure of atmospheric pressure or air pressure, which is so large that it was able to actually crush that steel drum. Isn't that crazy, Reagan? Air pressure can crush a steel drum? Yeah? All right. So you guys are actually going to do your own version of that experiment the next time you come to chemistry this week. All right. So I referenced this law earlier. It's Dalton's law of partial pressure. We talked about it when I looked at the composition of air, where it was 78% nitrogen, 20% oxygen. That slide is a good example of Dalton's law of partial pressures, which essentially Dalton's law is that the total pressure exerted by a mixture of gases is the sum of all the partial pressures of each individual gas in the mixture. So if you want to know the pressure of the air around you, you need to add up the pressure of nitrogen and oxygen and carbon dioxide and argon and all the other gases that make up this mixture of gas that's putting pressure on you. That's essentially what Dalton's law says. So we're going to go through a quick example problem together. You guys don't have this in your notes, so just watch and listen for now. This example problem says, what is the partial pressure of oxygen in a mixture of nitrogen and oxygen in which the pressure of nitrogen is 650 millimeters of mercury and the total pressure is 820 millimeters of mercury? So you're going to use Dalton's law, which says that the total pressure is equal to the sum of the partial pressures. And we can plug in our values from our word problem above. Total pressure is 820 millimeters of mercury. Nitrogen had a partial pressure of 650 millimeters of mercury. And then we're looking for oxygen's partial pressure. When we solve for X, we can figure out that the partial pressure of oxygen in this mixture of gas is 170 millimeters of mercury. So this is how much pressure the oxygen is exerting from that mixture. Okay? All right, now there are 3 practice problems for Dalton's law in your notes. I want you guys to do those and then go over the answers together as a class. After you guys do that, you are done for the day, and I will see some of you tomorrow. Say have a good day, Reagan. Have a good day, everybody. All right, don't forget to press that like button and subscribe. I'll see you guys later.